Okay, now the logistics are out of the way, and let us begin. So I'm going to talk to us all and myself. I'm sure I'll learn things in this about some of the macro-ish Scala 3 improvements. So they being the Scala compiler team at the EPFL, they've added a whole bunch of beautiful features to Scala 3 that allow you to do something like metaprogramming, but without digging into the full complexity of macros. Macros are cool, and I love them. And recently I've been exploring more Scala 3 macros, and it seems like it's finally starting to click, actually. So I'll probably do some more sessions on Scala 3 macros soon. Some fun ideas I want to try. But today we're going to look at just sort of the in-between world. A lot of these have to do with this inline keyword. And so we're going to start from there. That's kind of what's powering most of what we'll look at, or it's going to be involved in some way with everything that we're going to look at today. So let's just get started with a dead simple example. I actually made one little macro here that's quite simple. It's called debug inline. And so what this is going to do, I should explain, is it's going to take whatever code we ran or plopped inside of these braces, and it's going to print two things. Well, the line number. It's going to print basically just the code string. In case I scroll, that should just be the code string, unless it screws up. And then below is kind of the code string, but it's a representation of the code. It's like a pretty printed version of the syntax tree after certain compilation steps have been processed. So there's sort of the AST that's parsed. Well, first of all, there's just the string representation of the code, which is here. And then the compiler goes through phases, turning this into abstract syntax trees, typing those trees, processing them in certain ways, executing macros and other compile time operations. Any compile time operation, in fact, that's sort of important to talk about. Compile time operation is basically a function from an abstract syntax tree to an abstract syntax tree. That's kind of what a macro is as well, but we're changing these internal representations in some way, maybe simplifying the code, maybe just using a macro to completely make it crazy, turn it into a totally different abstract syntax tree than what you wrote. Right, with Quill, you'll have something like, query user dot filter whatever name equals John, and the sequel will get turned into that, right? At compile time, sort of. Quill will do something like taking that, what looks like normal sort of Scala syntax, but actually parsing out the syntax tree that's received from this, and turning it into another code string that's spliced back into your program. That's actually like going to be a prepared statement. So that's one example of macros. We're going to look at a very simple kind of compile time operation, which is inline. And inline kind of does the following. Let's just look and we can get an idea. So here is without inline. So this is the code string. This is what we see after certain compilation steps are processed. So we're sort of nearing the end of the compilation pipeline, and it's going to be generating some Java code out of this, or Scala JS code or whatever, and moving towards the back end of the compilation pipeline. By the way, I mentioned phases of the compiler, and it's basically these many compile time operations stitched together, where the output of one gets fed into the input of the next. And it's one place along this chain is going to be sort of running macros. So that'll be after sort of certain typing operations have occurred, but before, I'm sure, other complicated operations have occurred, and before it does the final JVM output or something like this. So we start out with the code string, do some kind of maybe there are tokens, and then a whole bunch of processing of the abstract syntax tree, tree to tree to tree to tree to tree. Okay, and we're just going to look at, I don't know exactly which of the many. I think there are like 23 phases or something. There are lots of phases. Or maybe 23. I'm thinking of the number of tuple overloadings in Scala 2. There's a whole lot of phases, and one of them is going to be what we're going to look at here. Okay, so here is just the output sort of near the end. That's kind of what I wanted to say, right? So after we've done certain things. So this will allow us to see what the effects of adding certain keywords here are going to be on sort of the difference between this pretty printed representation of one of the early syntax trees, essentially, or it may even be just the code string, versus something that's been processed a little later on down the line. Okay, so we're going to look at inline. So it's a soft keyword that you add to the front of certain identifiers, most commonly def here. And if I save this, remember what it used to look like. It now looks way noisier. So maybe I can actually put these next to each other, and I'll just make a copy, and I'll call this inline business and do business, inline business. And I'll just make this larger, and we can take a look at what's happening. So here's inline business, and inline business looks really ugly. If we peek into it, though, what's actually happening is that this is the print line method. So this is actually sort of the code, a pretty printed representation of the code inside the body of the method. And unfortunately, when printing it this way, all of the method identifiers get fully qualified. That's why everything is super noisy. And also, implicit conversions like string context also get applied and printed here. So some implicits that are active here are being rendered as well. So it's a little noisier. Maybe I can make that less noisy by not using my fancy .blue helper. Still quite noisy, but you get the idea. Maybe I could actually just make it really simple by just returning the number 999. So there we go. Now it's really simple. Inlined, we get 999. Not inlined, we get the call to do business that we see here. I wish I could jump around a little less, but yeah. So what does inline do? Well, the AST transformation is that when you're calling a method at compile time, in one of these steps, the Scala compiler sees the abstract syntax tree for this method call. And if that method was an inline method, well, then the Scala compiler also has access, as you might imagine, to the syntax tree of everything inside of that method's body. And so then it just basically copies that body out and replaces the method call with it. It inlines the method call, which I'm sure many people are familiar with that optimization. You know, famously the JVM, just-in-time compiler hotspot will do that sort of as your program is running based on runtime information. But this is very much a compile time inlining, and you opt into it. And in Scala 3, you are guaranteed that this will always be inlined every time you call it. So there will never be an inline business method call. This is purely going to be it's always going to be erased at compile time, and only the code inside of it will exist. So far, that seems okay, cool. What's the point of that? I mean, it's nice to be able to inline things. Scala 2 had an inline annotation, which was supposed to give a clue to the compiler to hopefully try to inline things if possible, but only for performance reasons, really. Remove the allocation of the performance of a method call, and just put the value in there. And that doesn't always work out as you'd like sometimes anyway, performance-wise. But this is not really the point of inline in Scala 3. It's not just to erase a method call. That would be very boring, and that would be a really long hour we'd spend if that were the only interesting thing. But it's the beginning. And yeah, we'll see. It's hard to describe abstractly. We'll see what cool things this will allow us to do by being able to sort of just get the body of a method inlined like this. Does that make sense to everyone? Definitely, I have the chat open, so the Zoom chat I should mention. I know usually I say use the Discord chat, but now my screen is so big that I can put the chat in the corner and it doesn't take up everything on my screen like usual. Okay, great, thank you. Sweet. Yeah, pretty simple. We'll move right along. Okay. So here's something else, another feature that's kind of cool. Where am I going to go? Oops, run main, and then let's do recursive what did I call it? Inline power example. So this is taken straight from the inline documentation. Some of these examples some of them are not at all, but this one is, and we'll tweak them all. But this one's a good one. So it's just another inline method, obviously more complicated than before, but we're going to see what happens when we call this inlined power method. First, let's see without the inline. Oh, is everything okay there? Have I broken something? I don't think so. 3. What is this? Class loader from class. Inline running lab. Let me try that again. Oh, wait, because there's no main. Did I delete the main? I did. Okay, there we go. Now there's a main. Now it's calling it. Great. So without inline, we're just calling this power method and we're passing the result to print line. And so we see 125, 5 to the third power. Great. But if we do make it inline, we're going to see something very different. Note, the important part here is that this is a recursive method. Power calls itself. So what the heck is that going to do? Well, if we look at the result here, we'll see that it did actually inline everything. Oh, wait, I've called the wrong method. Inline recursion. Well, looks like I'm calling the wrong function. One sec. Inline recursion example. There we go. Okay. 2. There we go. 3. All right. So now it's the right output. Sorry about that. I don't know what was happening. Okay. So with the inline keyword, we see now the body of is this right? 5 times 5 times 5. Yes. Where's the print line coming from? Oh, duh. That's coming from. Maybe I'll wrap the debug inline with the print line so we don't see that. Good. Okay. A little simpler. Okay, so the code string's power 5.3, and the result that's actually the code that's going to be passed along to later stages of the compiler is first assigning a value y equals to the number 5, and then multiplying y times 5 and returning that, which is kind of interesting. So this is the body of the method, right? So this one's doing a lot of crazy stuff, actually. Because we don't see any of this. We don't see the ifs. We don't see, it sort of starts on this line in an else statement. But clearly these ifs are being executed because we do eventually terminate. So it's kind of wild. So basically what's happening is, well, it is recursively inlining. So right, first we pass in what are the parameters? 5 and 3. 3 is the important one that's sort of guiding our recursion here. So first we get 3, so we're going to skip the first 2 cases, and that's why we don't see a 1 or an x anywhere at the top. And then we come down to this line, and we say val y equals, okay, great. So that val y is going right there because this is the branch we're in. And then we're going to basically inline whatever is in here, the recursive call, which is going to be 3 divided by 2, which is going to go down to 1 because we're doing integer division. It's going to kind of floor it. And so then we're going to recurse. And if n is 1, well, then we should just return the number 5. And that's exactly what we get. So this recursive call turned into 5. And then we continue along saying, well, once again, this if has been erased. So what is the deal with that? We'll get to that in a minute. But in that case, so we pop back up to where we were. We had 3. So 3 divided by 2 is not, 3 is not divisible by 2. So we're going to go to the else branch, and we're going to get y times x, which should be the result that we had previously, which was 5. So 5 times 5 times 5, which is indeed the result. And this is kind of an optimized version of powering, where we're sort of taking advantage of the composition of, I guess, exponents by dividing the number and then just multiplying it by 2. So we're making it logarithmic in computation time rather than linear. But it makes it a little more confusing. But nonetheless, that's kind of cool. First of all, we're doing a whole bunch of stuff at compile time. Let's make this number a little bigger to get some more recursion. And we'll see that it just keeps nesting. So we made it large enough now that we have 3 sets of recursion. So the first time when it was 3, there were just two layers of recursion. So we saw that val y on the outside, and then the recursive call just returned a constant. So that's kind of what got inlined there. Actually, let me make it so it's just 1. Now the result is just 5, because when n is equal to 1, then we just return x. So we're just returning the inline is just returning that x. 3, we've taken this branch, and then we recurse to that version where n is 1. And therefore, this second recursive call to power gets set to just 5. And then we sort of use some of this code elsewhere, and so on and so forth. Let's keep going. 4. No, I need it. What do I need to do to get 3 stacks? Oh, did I get 3 stacks? There we go. This. Okay, so now we get val y equals, and then we get a whole block, basically, a typed block. So that's a common thing that's going to happen. We're going to see where you have basically the code and then a colon and then a type description there. So that second call now, where since we started with 4, it's going to be 2, therefore we're going to recurse again. So that second call just gets dumped out as a whole block. And basically the block in there is what we saw last time, where that inner nested recursion call, so that the third time we're calling power, that finally is a constant value. And then we just keep layering these things. So it really is just like, I know I've done it in previous symposiums, and I do it all the time when teaching. Like there's this, it's inlining, right? It's what they talk about in, what is it? The structures and interpretations of computer programming. Like if you want to understand functional programming, it can be really useful to basically take the body of a function and manually inline it. So, you know, I do that all the time. If you want to learn how like list concat works or something, or whatever, any method at all, x int equals x plus any method x. So if you're calling any method on 10 and you want to know how it works, well, I often say, or I often do this, is well, let's replace it with its body. And so it'll be, oh, okay, it'll be 10 plus any method. Okay. Oh, but then of course we have this any method call again. So let's replace it with its body. And then, oh, it's going to be 10 plus any, and so on and so forth. So realize that this is going to recurse forever. But that kind of series of steps is very useful just for figuring out code. And that's basically what the compiler is doing. It's just literally taking the body and inlining it and then simplifying it. So there was a question. So 2 questions. Yeah, let's start with the last one, which I kind of was just alluding to there. Yeah, what if it's an infinite recursion, or what if the number is just really big? So, well, 100 works because we have this logarithmic algorithm. It's actually going to work pretty well. But let's give it a really, really big number. Oh, damn, logarithms are hard. We're going to give it an int that's too big. I think it'll actually work with the biggest int. So if we make it less efficient, so another way of writing this function, if you think about it, would just be n minus 1, and then just do x times y. So we'll just multiply it by x so many number of times. We could even just simplify to 2 cases then. But yeah, let's give it this and just with 1,000. And this is going to blow up. It's going to keep going. And then, well, so what actually happens this last time, recursive inline dot power. Oh, that's interesting. Oh, that's actually really cool. So once it would stop, it ceased being able to inline, and then it looks like it actually called the method normally. Unfortunately, this is also a compile error. I'm not sure if that's just because of my settings. It should be. Yeah, so I'm getting a whole bunch of weird stuff. But no, there's the actual error. Maximum number of successive inlines. So 32. So you got to make sure those recursive methods have pretty good time complexities or are written logarithmically, and then these should be good. Otherwise, a bit of a danger. There's another question. In inline def power, I'm a little bit surprised that n could be any int and not an int node compile time, but I suppose incorrect use is detected at call site. So yeah, that's actually something I want to talk about. It can't be any int. You're right. You shouldn't be surprised. It's just that, yeah, it's determined at the call site. So let's take a look. Let me first make this back to the efficient version of this. When looking at the example, I actually wasn't sure why they were going with such an efficient representation, but I realize now it's so you can basically, well, I wonder if this will work. Maybe this will be a good time to show. Oh, no. Okay, yeah, we successfully get infinity. Great. Anywho, it's also funny that that seems to work. Or does this fail again? No, that seems to succeed. That's cool. So it clearly knows that int max value is a particular number. Yeah, knows the type of it. So it can just inline that as well. Okay, we'll talk about that in a minute, but that's kind of cool. Let's make these smaller numbers. Okay, one last question. What about inlining of 2 mutually recursive functions? I would assume that would work the same way. And let's test that in a minute. That's what I like to do. That's super fun. So let's test mutually recursive inlining. One sec. But first, yeah, let's talk about some things that are happening in here, because it's kind of crazy that, first of all, a couple questions come to mind, I'm sure. What I said, the ifs are gone, and the ifs are clearly gone, but why the hell are the ifs gone? That's cool that the ifs are gone. And secondly, yeah, what if you use a value here that it says I can just put has any double, but how would it even inline that recursively and know where to stop? If doesn't it have to kind of know the value of at least n at compile time? Because we're sort of checking against that. How would it know if this were a runtime value that was received from the user? There's no way it could inline this, right? And yes, you're right. There's no way it could inline this. So let's simplify this just by making a value x called 100, or let's make it 3 even, and pass x in here. And we'll see right away that, yeah, the maximum, well, this is actually a weird error, and that doesn't really make sense to me. So I feel like they could work on some of their error messages, because that is like, why did it keep recursing? That doesn't make any sense. What you're supposed to do in this situation is actually, if you want to enforce that these values at compile time, sort of, you could inline that int. So I think, will that give us a better error message? No, that's still not going to give us a better error message, actually. I'm wrong. So yeah, I feel like that should just be an error message. You do have to know this at compile time. The real way to fix it, and what's actually happening for free, if we know this at compile time. So if I put a 3 there, what's actually happening is these ifs, the reason why the ifs disappear is that there's also an inline if. And inline if. Okay, I don't think I need to say inline else if, or maybe I do. Oh geez, maybe I do. I guess so. I'm not entirely sure, but it'll probably trigger with just one of these. I'll just keep it at the front for now. So now if I use a value that cannot be inlined, what'll happen? Yeah, so now it's going to say that the location contains code that was inlined. It cannot reduce the inline if, essentially. So this is the error message I think you were looking out for, Phil, which is could not reduce inline if because its condition is not a constant value. I don't know what the x equals 0 thing is. It doesn't have to be 0. Oh, that's because it's the check that n equals 0. So they just renamed. Okay, that's actually kind of cool. Is that correct? Let me just validate that that's true. Where's that? I should see the 5 now. Yeah, okay, cool. I see the 5 now. Well, that's nice. So it turns out, and I'm not sure if I love the behavior, but it's kind of implicitly an inline if, or maybe it's just a behavior of the compiler where it'll always try to inline. I mean, it's a common, all compilers tend to do it. It's just that it's just purely a performance optimization. At times they do some form of inlining. So maybe it's just sort of the normal inlining is done if it knows the value. But if you want to be absolutely sure that you get the inlining, and we do in this case because we're in an inline method, you want to add that inline keyword. And now we're going to get a good error message. It's kind of like, I think, when you make a tail recursive method, you probably want to put that little tail recursive annotation on it, just so if your method becomes non-tail recursive, you get a compilation error. So it's kind of, it seems akin to that to me, where you don't need it, but if you want to be notified if this inline is, if this if is no longer being inlined, then you probably want to put that there. Okay. Sweet. So let me make this a 3. Let me change this to the x. So yeah, it's totally fine if this double is not inlined. We do not really care about this. And actually, I want to test something real quick. Okay. So it looks like we need an inline before every if then to get that error message. I was just testing that real quick because x is now a variable and it's not known at compile time. So we looks like you have to have a lot of inlines. So the real safe way would be to have it for between every time you use if, not the else, obviously, because it doesn't need any. The compiler isn't testing against any values at that point. So yeah, that's what's happening at compile time. It has all the information to both make the determine which branch to take, and then it's just going to throw away all the other branches, and that's why our it's not the right thing being printed. There we go. Is that right? Yes, there. Now it's right. I have many examples in other files, and it looks like it's running the wrong thing sometimes, but okay, good. So yeah, that's why there's no ifs. That's what I'm trying to say. It starts with a, let's do 1. Wait a sec. Oh, of course. Okay. And now this is interesting. Because I changed the number that we knew before to X, well, a couple of things have happened, but internally it's being referred to this X proxy value. So that's also an interesting thing that's happening. Also, it's being turned into a double because we gave it an int. So you also see the implicits in this expanded view. Let me make it back into a normal value. There we go. So the ifs are being thrown away because they're evaluated at compile time, because we know, the compiler knows what exact int this value is, which is cool. Okay. All right. And let me actually, I'm assuming mutually recursive inline will work. If anyone wants to try that out in the background, I'm just for time reasons, because I don't know how I've already gone. So 30 minutes, but maybe I'll speed up a little bit. But definitely try this and paste it in the chat if you get an answer. I'm sure it would work. And yeah, oh yeah, take care. Does this have a lot of does this have a lot of utility over just letting the JVM JIT inline dynamically if it is worth it, or is this a feature aimed at non-JVM Scala implementations? So yeah, we're just sort of so far to stage 1 looking at the power of this inlining. It's not really used for performance reasons. I mean, it could be used for performance reasons. If you really know you want to inline something, it'll inline, then that's great. You have the power. But the real power comes from the fact that we can play with types in this level too, and it can let us do some other interesting metaprogrammy sorts of things, and we'll slowly ramp up the complexity. So let's move along, because yeah, we're sort of at just the lowest level mechanics so far. Okay, but yeah, I think you'll see soon the actual really cool stuff I can do. So this is just another sort of like implementation detail, if you will. What did I call this method? Inline argument example. Okay, which didn't do that. Lab dot pages dot this. Okay, and let's make a change here. Good. So what's happening here? What are we looking at? So this is another sort of example taken from their doc, slightly simplified, but there's some method that takes 3 argument types. Just a normal by value argument, a by name parameter here, and then another inlined parameter. And so we didn't talk much about the fact that you can put inline also on parameters. What does that mean? So we're going to look at what sort of inline definitions do with each of these 3 argument types. And so we're just calling this method with these 3 arguments, and we're just passing 3 methods along. So we can see, how does it deal with these 3 method calls that we're passing along here? And what's happening is, well, let me actually go here. So first of all, there's no call to funky assert equals any longer, because it is, actually, let me remove the inline first so we can just see what the heck's happening. Oh, well, then I can't use the inline modifier on the inside unless it's inline. So yeah, we're just calling this method funky assert equals with 3 different arguments. So when we inline this, the first thing to notice is that that method call is gone, because it was performed at compile time, if you will. But instead of just being, just sort of the 3 method calls in here, it looks like the Scala compiler actually extracted some definitions. It made a block around the method call and pre-computed these 2 values. It made a value definition, it made a def definition. And just to contrast, what if I just passed in the numbers 1, 2, and 3 here? We would just see 1, 2, 3. So nothing special if there are sort of values at compile time. But if there's something else, and I wonder, actually, I'm just curious, if they're values, does that matter? I don't think it matters. Oh yeah, and if they're okay, that's cool to know too. If they're just values, it also won't do anything special. It'll just plop them in there. So it'll sort of do the normal inlining behavior that you'd think. This is basically just a macro. When you see this code, replace it with this code. Just shuffle the arguments around. But interestingly enough, if these are method calls, it does something different. And it inserts these other things. So the first thing to notice is actual proxy. So really the only thing is it's basically taking this actual value that we're using just as a normal parameter, and it's assigning it to a val. To the parameter compute expected that we're assigning to a by name parameter, it assigns that to a def. And then it just uses those now proxy names inside of the function. So it just takes the variable name and adds proxy1 onto the end, excuse me. Have to cough every once in a while. And for the inline version, it actually just grabs the code that you put into that argument position. So it doesn't assign any proxy to it. It just, well, it inlines, it takes the literal code you put in here and drops that inside. In fact, if I do this +5 here, we'll see that that entire code block got just plopped in there. So when you inline a parameter, you're basically copy pasting this into every reference. So it kind of acts a little bit like you'd expect a by name parameter to, where except now instead of every time you reference the value, it doesn't call the by name parameter again like a method, but instead it copy pastes the entire code string again. So notice how every time we refer to delta, we get literally the code string we pasted here, which is actually important kind of as a nuance. If this were you know, some kind of block that printed this and then returned 5, well, now we're going to print multiple times on the inside. So yeah, fun, weird stuff. Yeah, so why? Yeah, so let's talk about why is it doing this? Why is it doing this? Let's go back to the simpler example. So, well, if you think about the behavior you want, if we refer to a by name parameter multiple times, we would want it to be evaluated multiple times. Those are the semantics of by name parameters, right? A by name parameter, it's really just so in normal cases, right? Example, x is an int, and I'll just say print, I'll just refer to x twice here, in a tuple. And I will call this at the in here, so we can look at it as well. And I'll say, oh, I have to call this method, sorry. Print line, hello, getting 5, and then I'll just return 5. So that's the block we're passing in. And we just see we see getting 5 printed once. I'll make that red. So there we go. Getting 5 is printed just once. If I make it a by name parameter, it's going to actually print getting 5 twice. Every time we refer to x, it's going to reevaluate the code we passed in here. And so it's actually, what this actually is, it's actually basically behind the scenes a thunk. And it's just being called every time we reference it. It's being called every time we reference it by its name, which is kind of why it's called a by name parameter. So when we reference its name, it's calling a thunk, a secret thunk. So it's basically a syntactic pun. I kind of like it because it's just basically, if this were a thunk, you'd need all these parentheses everywhere. But by deleting the parentheses, it has the same behavior, but you just don't need the parentheses. So that's kind of fun. And then also, if we actually needed a thunk, we'd have to do this. And really, the whole point of by name parameters is just to get rid of the we need to do, sorry, this. Get rid of the awkwardness of having to make all these functions everywhere and just get that for free. I think I'm not, oh yeah, because this expects now one of these. Let's see, if we wanted a real by name example, or this to work, say we didn't have by name parameters, we would have to make this accept a thunk or a function, a nullary function, essentially, call it 3 times, and then create a nullary function out here. So it's pretty awful. So the syntactic pun is, what if we just do that for the user? So we have a prettier language with less boilerplate, and we just get these lazy values like this. Okay, so that's the behavior. If you didn't know what a by name parameter was, that's basically what it is. And so every time we refer to a by name parameter, we want it to be reevaluated. Getting 5, getting 5, getting 5. Yeah. Or generally the magic is it's only referred to if you, it's only evaluated if you refer to it at all. So now it will not print getting 5 at all, versus if this weren't by name, it would print it always once because we're evaluating this block at the call site. So usually you don't use a by name parameter to evaluate something multiple times, but rather to prevent evaluation if you do not refer to it. And then it's oftentimes you'll make something like this. So if you are going to refer to it, at least it's lazy and you cache the call. Okay, that's the full explanation of by name parameters. But the important part is the default semantics are, if you refer to it multiple times, each time you refer to it, it's like calling a function. Okay. Which means if we now go back to our other example of whoa, where's my debug? So now I'm referring to expected twice. So if this were a by name parameter, we would expect that expected gets called, maybe I should rename that, but whatever. We expect this gets called twice, evaluated each time it's referenced to by its name. And by predefining it as a def, that's going to happen. That's the behavior of a def. Whatever block of code you put in that position is getting assigned to a def and will be evaluated twice. Now, if it didn't make these proxies, and similarly, if you just have a normal value like actual, you would expect it only gets evaluated once when you call it. And so if I refer to actual multiple times, well, then it's going to refer to this sort of cached value multiple times. Why does it need this at all? Well, if it didn't have this and it simply just inlined the code string everywhere, well, then you would basically always be getting kind of by name parameter behavior. And so you wouldn't be able to not have this. So really and similarly, I guess the behavior could just be this inline behavior for by name, in that's kind of the behavior you get, except I don't know why they did that. Oh, I guess there are certain reasons. Well, the actual semantics of inline, there's this new axis we have to deal with, which is this what is available at compile time. So with an inline parameter, it's sort of by name-ish, in that if I refer to it multiple times, I get the whole block of code. It'll be evaluated twice if it's an expression, but I also literally copy paste the code string. Yeah. So we're going, these are little details. We're not the super, I find it interesting. I mean, it's fun researching these things to like learn things that are so nuanced that I wouldn't ever learn them otherwise. I would just kind of survive in slight ignorance. So if you try inline if something expected, let's try this. So inline if true, then expected. So then we're going to see expected. If we don't, oh, what am I doing? Then false. No, the proxy will not get nested. I think these proxies are created at the outside. So inline, let's take a look though. That's a great question. Use double, expected. I'll just give it the same name, double, and I'll just put it through like this. So what'll happen if I call use double and pass expected here? Are we going to get these nested proxies? Yeah. No, wait. Are we? No, we're not. What did we guess? We got something weird though. Actual, use double, expected. Is expected gone? Well, technically that's okay because it's okay. So, okay, interesting optimizations I think are occurring because technically it knows that we're never using the result. So maybe it's okay to do that. And it is a by name. Let's do use double on actual, and see what happens there. So that time it did not make a second proxy. So yeah, it looks like interesting things occur in different situations. Yeah, I made a second proxy. So yeah, I'm not sure if it's as optimized as it possibly could be. Like their versions of doing this inline, whatever the algorithm for inlining is. I'm not sure if it's going to say, hey, well, if you're already in an inline, then maybe we don't have to do the second proxy. I think it's probably best to just have like rules that work everywhere, even if they have some redundancy. And then, maybe a later step in compilation could optimize this inline stuff anyway. So that's interesting to know. But yeah, I recommend playing around. I can post this little macro if you want to have some fun with it. But let's keep going because I want to get some more exciting stuff. But this is fun, and I don't know. I like tweaking and experimenting and playing with the details and asking those questions that you've been asking me, which is like, what'll happen if you try this weird thing? So let's keep going just a little bit, and I'll give you the macro. It's pretty straightforward. I'll copy paste it into the chat afterwards. Okay, and the last thing I just want to show really quickly before we get into this is just sort of the last little piece of mechanics as transparent example. So we have this method called choose, takes a Boolean and returns either one of two types, baseball bat or frog pizza. And this is not from the official docs, or rather I changed the types. I think they were A and B or something like this, or A and some subclass of A. Anywho, and now I'm just choosing true and I'm choosing false. So let's see what we get. I have to make some change first so that recompiles and we can see the output. Okay. So we have choose true, we get the baseball bat. Choose false, we get the frog pizza. That makes a lot of sense. But there's one actually other thing. Let me remove this transparent keyword first. In the bottom right of all these code examples is actually the output type as well. So there's one last bit of output information. So clearly it's any, right? It's frog pizza and baseball bat. These are not related at all. So it's either one of these. However, if we add the transparent keyword, the actual output type is either baseball bat or frog pizza. So at compile time, we know the value and we know its type. It's our type annotation. We know it's baseball bat based on what we did. If I change it to false, it's sad now because it's the wrong type. And I can change that and fix it, which is super cool. And if you think about what's happening, I mean, not to trivialize the compiler, I'm sure, not a lot of macro systems have this ability. So I'm sure it's very complicated, but to some degree, it makes sense, right? Where this is all being executed at compile time. The compiler is pretty good at figuring out the types of things. That's what it does. So after it gets this value here and inlines, after it gets this step of knowing that, hey, the real body of this method is just baseball bat. It knows that based on the input. Well, then instead of going with the sort of the type that it had in this full statement that wasn't inlined, which would have been any, or the type description you gave it, it'll then update the type to be whatever the actual narrowest type, like if it wouldn't, how would it normally type the actual statement that was returned? That's basically what happens. And I should make this inline if as well, because otherwise it couldn't do that if it didn't know this. Yeah, so that's transparent. So you can get the types going, and you can imagine all sorts of crazy things you could do with that. But those are the mechanisms, and we'll try to look at some crazy things you could do. This is one last example from their docs that I want to show you. This is now a practical example. It's not the only flavor of examples that are practical, but let's go with this. And what is this name? Inline logger example. Lab.pages.inline logger example. Okay, so what do we have here? We have an inline logging method that takes a message that's inlined here. I guess it doesn't really matter for our purposes. And the op is inlined as well. Though, once again, we could go with like a by name or something. It's up to us. And if logging is configured, if this value up here is true, then we're actually going to log the message. And I'll make this an inline if as well. Or if not, we're just going to return the operation without logging. And actually logging will like print some log value. So it'll say it's starting, then it'll print the result that it got for the message. So if this logging config variable is false, well, then it should never log and we should just get the value out. And if we see what's happening, we'll see that the result here of running important code with a random number is actually, well, it's all this technically, but nothing is being logged. There's no printing happening. Because of what we just talked about in the other slide, it actually looks like it's going to, this is another case where they could probably make some optimizations if they wanted to. but these arguments were never used, and it's an inline method, but they were still both assigned to things. So there was a def. Obviously, the def isn't going to actually do anything. So even though some things are erased internally, the arguments still behave by those sort of those properties that we just looked at before, where inline arguments are assigned to a def and value arguments are assigned to a val. And I think that's reasonable. I think that makes sense, even if they're technically not being used. If you want them to not be used, well, then you can say inline. Excuse me. And then there goes the first one. And if I wanted the message to go away, well, I could say inline. And then there goes the second one as well. And now all we have is literally calling important method and none of that proxy setup. So if you really want to get rid of those things, now you have the power, depending on how you write it. But okay, that's interesting. We haven't actually turned logging on yet. So what'll happen if we set this value to true? Well, if we do, then we actually get the logging code. So now it's going to actually call, basically, actually log. So it's just calling actually log, right? It's erasing the whole if conditional, and now it's inserting the code string for actually log here. Set it to false. It's just the value. So this is a way to sort of, you can have a library, and you can only turn on logging in debug mode. That's a great point. Just as I said, it's actually slightly convenient. Nabil said, is this really practical? I mean, who turns on off logging before compiling and not reading it from a config? That's a great point. I'd imagine there's something clever you can do, but maybe staged compilation. But in certain scenarios, maybe it could be useful. But yeah, good point. I just want to see something real quick. Does making this def ruin things for us? If it's true, it'll log. If it's false, it won't log. So cool. It could also be an inline def, which makes sense. Inline vals have certain restrictions. But I won't get into those because I've gone through too many nuances. But if I make this just a normal val, now it's not going to inline the location of config.logging. So another use of inlining things as well, another purpose to inline these arguments as well, is that without inlining this, what the compiler is going to see is it's going to see this expression logging. It's just going to have like an AST representing calling logging on some object. It's going to be like a select node, and you're calling the logging method of config. It's more complicated than that, but basically that's what it's going to see, the AST for that. It's not going to know the value of that AST, right? That's a runtime thing where the actual call to logging that's done. But if it's an inline definition, another reason to use it is that then it can be used internally in other inline sort of places. So now this is kind of it's not transparent in the transparent inline sense, but this basically just gets de-aliased to its actual value if it's inline at compile time. Yes, you can compile different versions at different log levels. Yeah, exactly. I think maybe that's the one reason, the one way it could work. Yeah, something on my to-do list to learn about is that staged compilation. That there's something else they have there about staging macros, and maybe you could like read a file before compiling part of your program and then pass that along. I have no idea if that's the purpose. I am completely ignorant with regards to that. But here is a more useful, at least, than the other examples we've looked at, even if maybe you wouldn't exactly do this in your program. But maybe you want to add debug testing. Okay, one reason I can imagine actually is on Zio. Zio has a very complicated runtime system, and you don't want to add logging everywhere for Zio development purposes, because that will make Zio slower for everyone else, all the users. However, perhaps you could have a little config here, and when you're working on Zio yourself, you can turn this on. So maybe for developer convenience, that's one way that this exact feature that has to sort of be hard-coded in the library. Yeah, you could turn it on just because, well, I'm the developer and now I want to turn on development mode for me. So that could be cool. I'm not sure if John and Adam have considered that, or if that would even be helpful. But if they ever watch this, no, I'll recommend this to Adam. Oh, by the way, Adam will be back next week. I forgot to mention that at the beginning. Adam's traveling. He's okay. And he will be back with us next week. Okay. Okay, now into some more fancy things. That took longer than I assumed. It often does. I tried to be less frenetic than usual and actually spend some time on each example. So maybe we won't get into as many exciting things, or I'll go a little longer. Hopefully people are okay with that. But let me know. I'll just show off some examples and stop going super into the weeds of the details. So this one I actually don't need to even compile, because we're not going to really be looking at the runtime output anymore. To string.read, let's make this big and bold so we can see it. So here it is, 11. So what is happening here? Well, one thing that Scala has are these things called singleton types. And these, I'm not entirely sure if that's the right name for it in Scala 3, but here I have some number, int 11, right? So the actual type isn't int for this. That's kind of a widened version of the type. If I do not ascribe a type, we'll see that, oh, maybe we won't see that. Okay, I'll have to give it myself here. But actually the type of this number is 11. Singleton or literal types, yeah. See, no, that's sorry, I'll read your comment out loud. I shouldn't just respond to comments without reading them because I don't think it's visible on the screen. So, but you could also have a ZO debug version of the lib that you can use for in your code to find strange behavior. That's true. I wonder how difficult it would be to publish one with a true and one with a false. Can you automate that? But that would definitely also be cool, where you just easily strip out all those debug statements using compile features. So yeah, the actual narrowest type of 11 is the number 11. So certain special types like string and int and Boolean, basically sort of all the standard primitives, they have their own singleton values. So you can kind of think as Boolean, for instance. I actually think we've done this example in the past, but if you want to make a custom Boolean, you can always do it with a sealed trait of Boolean, and you can have true and false. And so, you know, case classes, case objects are each going to get their own type. So you're going to really get, you've probably seen this before if you've done a case class, right? Where true.type is actually the type of true. And sometimes it's annoying because you just want to have the type look like true. And sometimes people then say, well, type true equals true.type to export that for reasons. But if you actually were just to type true here, true, you would, if I can type it, why is it sad? Why are you sad? Oh, duh, true, because true is a keyword. It's an important word. It's true.type, and val false is going to be false.type, right? And if you're making a library, you often want to widen these things, and you don't want the user to know about those silly things, so you widen the type. But basically, that's kind of the behavior you're getting now in the type system. And in Scala 2.13 as well, these singleton types existed. So if you wanted to, I think the default behavior for when like inserting a type is to not do the singleton type, because that would be annoying and it wouldn't be very helpful code completion, because you seldom want to have all your values, you know, be that if I say val is true, and then, or whatever Boolean, and then you say true here is the starting value. Well, you probably don't want it always to be true. Maybe it's a var or something. But nonetheless, that is an aspect of the type system. So you have these types that basically represent values, and it shouldn't be like, I don't know. I'm going to insult a past version of myself, or not insult, because I think maybe, hopefully other people are there, where for some reason, while this mode of thinking doesn't necessarily make sense, compilers are complicated magical machines. And if you don't work with them often or do a lot of compile time things, the whole compile time runtime distinction seems insane. And can be, you know, the boundaries can be wishy-washy. And so I think for a while, like when I first saw singleton types, I was thinking, how is that even humanly possible? How does this ascribe to the laws of physics? Well, it shouldn't be that mysterious old version of me, because a compiler is just code. And in the compiler, they have case classes and sealed traits representing types. And if a programming language can represent numbers, well, if it's representing types, those types can have numbers in them, and they can do anything else. You know, there are other languages like Agda or Idris that allow you to sort of do like any kind of, any value you calculate can either be a type or a value, and you can just treat them interchangeably and just dance around. in the flames of mathematical categorical righteousness. And it's super, super cool. And it helps to tear down those distinctions a little bit. But there's nothing magical about it. It's just a number. It's just a value in the compiler. And yeah. And if you just have a value in the compiler that's available to you at compile time, well, then maybe under certain conditions, at compile time, for instance, you can then take that type level number and just turn it into a value level number. So that's how this is a type description, right? If I put an int here, we're going to get an error saying, well, int is not a constant type. So I guess that's what they call it, constant types. But 15 is a constant type, and we can print this. A string true, or why am I saying true? Hello there, hello from compile time. That's a constant type, and so is true and false and certain doubles and bytes and whatever other things. So we can get those. You can get those values as well. You can compute with literal types in Scala too. I think, yeah. Can I just do plus? So I think I need to import some other library, right? Or compile time math ops. Yeah, there are also mathematical values, which is pretty cool. So yeah, pretty fancy. True and true. Do I have and? I think there's another library I need to add. True and false. Yeah. Okay. Well. Anyway, you get the idea. You can pull values out of the type system at compile time. Obviously, they need to be known. But you can do some other things as well. So I can say also x.type, right? Can I say x.type? Oh, not a constant type. No, if I say 12, then I can do that. Okay. So yeah, I think you're right, Juan, that the compiler never infers a singleton type and you must describe it. That would make this example make sense. And it seems like a reasonable behavior. Okay. It is 6:01, but I'm going to go just a little longer because there's some more exciting things to look at. Yeah, maybe I could just continue next week because there's a lot of stuff. Let me do one last thing because I want to look at match types and the magic of tuple because this is where it starts to get a little fancier. So do one last thing, and then we'll get into the cooler stuff next week. And as you can see, my examples are degrading slightly because I was running out of runway. So I have a lot of testing that I will condense for next week into more prepared examples. But let's talk about the all new Scala tuple. Cool. So tuple. So we have 1, 2, 3. That's great. And we have tuple. And if I insert a type annotation, it's going to be int. But a tuple now actually acts more like a list. It's sort of like if you're familiar with an HList, a heterogeneous list. A tuple is basically that now, or at least supports those powers. And if you didn't know what that is, don't worry about it because we're going to see what that is now. So what is a list? Well, you either have a head, or sorry, you have two nodes, right? You have the cons node, which in Scala is that, right, where you get to add a new value onto the end of some other list. And that list eventually terminates in, the nil. So you have this ability to add a value to a list. Well, what if you had the ability to add a value to a tuple? And now you do. You have this operator here, which kind of looks like, cons and tuple. It's another sort of syntactic pun where it's a bit of the list cons operator, but also a bit of, the product type, product equaling multiplication, equaling like tuple is the canonical product type. So times and colon. Anywho, but the cool thing is that this also transcends. I'm starting to make up words now at this hour. It also goes to the type level. So I can actually, this sort of literal tuple syntax is just, syntactic sugar for essentially, well, it's not really syntactic sugar, but you could also write it like this. Of course, now we need sort of our nil. And now I don't think that works. Yeah, there's a special nil called empty tuple, fair. And that's going to be literally the same thing. So you could express it this way, tuple 2. I could have also just done, hello, 1, 2, 3, empty tuple. And each of these obviously can be a different value, 3.5, 3.5. And then we can type that and type that. So that's pretty cool that you can do that. Also, they sort of surpassed the limit, the upper limit, that magical evil ceiling of 22 tuples. You can now go beyond it, which is cool. But yeah, that's great. Amazing. But what if we also could do the following? What if we also know about these types, right? What if we narrow these to their singleton types? Well, that's pretty cool too. So now we have not only a tuple of values, we have a tuple and we know exactly what those values are, like the types of the values exactly constrained. Yeah, tuple and empty type are different. Empty tuple and unit are different. And I think that probably makes sense for reasons. Well, I think just for compile reasons, that you can actually look at the implementation of tuple and you can make your own yourself, actually. Maybe that's something I could do next week to do. I was actually going to do it this week, but I spent way longer on tuple from scratch. Yay! But yeah, it's probably good reasons why things might act weird. We could always make an implicit conversion. Okay, but then to tie things together, the last thing I want to talk about is one last inline feature. So we looked at const value, which you can pluck one of these constant values out of the world. Well, it would be cool if we could maybe pluck a constant tuple out of the world, and well, that's possible too. There's a method called const value tuple, and then I can throw in not that hello val results, and cool, and then I'll just do a main def, what should I call this? Tuple example. Thank you. Res print line. And then let's run this. And there we go. Yay. Res to string dot red. There it is. So yeah, that's cool. We get the whole value from its type, right? So we never had the values. We're getting the value from its type now. So how does that work? Well, it turns out we can actually implement this ourselves using one last cool feature, one last compile time operator. Like we've already learned almost everything. Well, we'll see. Okay, so let's have my const value tuple. And let's write this ourselves. So first of all, we need the tuple value. So I'll call that T. I usually don't like T. No spoilers. Go away, Copilot. He's spoiling fiend. No, disable globally. Good. All right. I'm not sure if it got it right. I didn't see it. Why is it still there? On guard. Are you active or inactive? Turn off. I think it's dead now. Better be dead, or I'll just have to type really quickly. It's dead. Okay. We're on our own. All right. Lovely. So first we need a type here. So turns out tuple is a trait. Yeah, as you can see, a tuple of arbitrary arity. And so we want to have some T that is a subtype of tuple, and that's basically what we're going to have. In fact, we're not going to have any value arguments. It purely just takes a type. And then we wish to return an instance of type T. And this needs to be inline, actually. Now, we kind of want to do the following thing. This tuple can be one of two subtypes. It can basically be a trait tuple. It can either be this cons node, essentially, and we'll just call it, cons, A onto a tail, which is another tuple, or it can be empty tuple. So we kind of want to match on both of these cases. Yes, we want to match in both of these cases. Actually, before I make this return the tuple, I'm going to have it return a list of any. That'll be slightly easier to implement. And then we'll take a look at the other level. Okay, so we want to match in these two cases that it could be. Either basically this case of the head and the tail, or just the empty tuple. And how do we do this? Because we don't have a value to match on, right? In Scala, when you match on a value, you need a value to match on, right? And you say value match, and then so on and so forth, case, whatever. And I kind of want to match on these two cases. Well, I actually just can match on them at the type level, which is interesting. So let's just pretend we have a value for now and just write how we might look at these at the type level, head, tail, and then case empty tuple. Spelled correctly. Great. Of course, there is no value, but there's this thing we can do. You can have inline match statements as well, by the way, and it would just be like the inline if, except you can have more clauses, and you can match on these sorts of these values that you know are compiled on these constant values. So if I had an inline and an int, I can match on the different values of int. But there's this other method called erased value, and you basically only use erased value with an inline match statement for the most part. I can't imagine another reason to do it, because all it does is allow you to basically, it's built to use in this case, because it pretends that there's a value here so that it compiles, but you can never use that value because there isn't really a value there. But it allows this sort of syntactic constructed type check, and it allows this type matching to work. And it's all inline as well. So whatever branch succeeds at compile time with the type information is the one that we're going to continue along with. So now we can implement this method. If it's an empty tuple, we can have a nil empty list. And if it's a cons node, well, these are types. And this one, H, is just a normal type, and T, well, that's going to be a subtype of tuple, because that's kind of how this cons node works. Can I look at cons class? Can I go there, please? Yeah, so this is what it actually looks like. H can be any type, and the tail has to be a tuple. So I don't know why it's not showing this now, but the compiler knows it. So now I can say const value of H, and then I can cons that on to my const value tuple, a recursive call onto the tail. And so now let's say my const value tuple, which is not really that, it's a list, but we'll just print it out. And we'll run this. And now we have a list of hello, 1, true, and 3.5. And of course, it's a list of any. And even if we make it transparent, it's still going to be a list of any, because once you put multiple types in a list, it's still going to be a list. Maybe if it just had a single element in it, it would be able to figure out that it's a list of string or something. Oh, but if it has a single element, okay. If they were all the same type, hello. Yes, there is, we could make a tuple one. That's another sort of annoying thing about this, is that a single value does not count as a tuple type. So now if let's do one thing at a time. Okay, oh, it's still a list of any. Probably some details with the internals here, which is okay. That is okay. Anywho, because, so ignore that transparent thing. Maybe we'll need it in a minute, but okay, so now we can return a list of the values, which is pretty cool. We're iterating basically through peeling off the values in this tuple just as we would a list, because it essentially now is just like a list. And it's a list that we can iterate over at compile time. But it's really the same exact operations. If you've ever implemented from scratch list operations, this shouldn't be terribly confusing. We're just, rebuilding a type level list as a value level list, which is pretty cool. But what if we wanted to build a tuple? So let's do that. A T, for instance. Well, let's do this. Let's cons it onto the tail, and then let's change this to empty tuple. Right? That's just going to remain the same, empty tuple. The problem, of course, is that, well, it doesn't know these types. Let's cheat. Adds instance of T. Sometimes you have to do that. Sometimes you have to as instance of in these at these type level places, and it's okay as long as your code is correct. Don't feel bad about as instance ofing. It's still pretty cool that you can do this, and it all does make perfect sense if you think about it. I don't know why it's just not automatically able to do it. Probably because I'm actually not sure why that just having it transparent doesn't work. But it doesn't. I guess because empty tuple could be, I don't know. You think maybe it could in the future or something, but alas, for now casting works. And that's basically, now we have a tuple. that we've gained at compile time. So that's increasingly, this is not about performance anymore. This is about weird powers that we have. And I think let's come back next week, because we can look a little further as to like, okay, these are some cool weird powers. Is it really that useful to be able to summon a compile time list of types? I mean, it's neat. It's a fun parlor trick. If you run a weekly Scala seminar, it's something cool to, eat up an hour and a half on a Friday night. But I also like doing practical things. And luckily, this can do very practical, cool things and save you a lot of boilerplate. So basically, what this is used for, along with some other powers known as mirrors, maybe the headlining feature of why this is useful, is that you can basically derive at compile time implementations of type classes, the other kind of class. We have too many classes of classes in this class. So that's very cool. And we can look at that next week. Yeah, what I wanted to do was actually, I built a clone of Magnolia that I called Daffodil. But then I got all carried away down so many different rabbit holes and other some fun compiler explorations, including you can now make this much simpler version of zippable that will basically zip any tuples and flatten them, no matter what the arity is of either side. And it's actually a very terse implementation. And it totally works as well. Run this. So everything is kind of working in unison here. So that's cool. That's a cool thing for maybe Scala 3 version of ZO. We could add fancier zippable capabilities. But let's get back to it next week. We'll have a whole bunch more time, and we can look at actually using some of these features. But yeah, I talked about inline match and inline tupling, and now it's 6:15. So it's been an hour and 15 minutes. Not so bad, and only a couple people have dropped off. So I'll leave on top. Yeah, any last questions though? I mean, I'll stick around for anything I could possibly answer, or comments. Feel free to unmute yourself if you want, or just type in the chat. Oh, what did I say was sad, Nabil? I missed it. You said, why is that sad?
I guess not a lot of people dropped off because the titles get already most of them away and they didn't come in the first place.
That's it. Yes, alienating early is the best trick in the book. And the people who remain are, yes, they're special.
I'm quite grateful that you've gone slowly, because I've read this stuff on the website 3 times and then realized a week later that I'd forgotten it all. So
oh, thank you. Yeah, same. And committing to doing this really helps cement it in my brain, at least for the next week or two. But I think it's finally starting to click. So yeah, thank you. I hope I've saved other people the efforts. But yeah, I appreciate that a lot. Okay, well, take care, everybody. Feel free to leave. I'll be here though if you have any other questions. Yeah.
I just one remark. Like while I was playing a bit around with the stuff, I think one thing that you come across when you try to do more complex stuff is the thing that you encountered at the end, right? That you had to cast to the T. Yeah. I think there are still a lot of stuff where you go behind the simple examples in the documentation that you encounter some rough edges, and you have to do some explicit stuff that you think yourself of, like, yeah, do I need to do that? Can the compiler not do this for me? So I guess an essence of all the stuff is it works, but it has sometimes some strange limitations, some of which you can avoid by doing things explicitly, like the casting, and some things that you cannot avoid and not configure. So, for example, I tried to do some match types to define like a range of ints. Yeah, and this works for only like a very small number of ints. and after that, the compiler says like, yeah, no, too many recursions, and I'm out, and you cannot configure the compiler to do more recursions or something like this, and the number is quite small.
Yeah, I think it was like 33 of those recursive or something. Yeah, way smaller than even the stack limit.
I think in the match types it's even lower than 32. I think the 32 is for the inlining. In the match types, I think it was 15 or something like that.
Okay, that's interesting. I mean, maybe that's, that's probably smart, knowing that Scala's history of like compilation performance issues because of people going crazy with compile time computations. So maybe they want to limit that. Make people think extra hard. But also, I think maybe this just comes from my experience with sort of the innards of Zio, where the outward facing API is pure and beautiful and functional, and it type checks and it infers. But on the inside, there's a lot of casting and any's for performance. This isn't quite for performance reasons, but if it's the only thing that I think there's some cases, like what we just looked at, which is like, I think that it could figure this out. It seems to work with my intuitions of how transparent works, but looking at the actual implementation of const value tuple, it's the same thing. They just have an intermediate variable, and then they have an end clause. So they clearly need to do it. So I guess we clearly need to do it too. But yeah, hopefully it gets there. But in the meantime, there's definitely some cool stuff where if you just think of sort of the type level computation as just a parallel nice thing to have, and then just make sure that your actual computation aligns with that, and have testing sort of similarly to how basically Zio does it. The innards are not type safe because it really can't be type safe. Theoretically, maybe some of this could be more type safe, but this is still a powerful pattern, and I wouldn't shy away from it necessarily. But hopefully it's the compile power spreads outwards forever.
I totally agree. It's like I don't say like it's a bad feature or something like this, but I think there is some immaturity, I would call it, and I of course I hope it gets better over time. And I think so they implemented it in a way that it's usable for the most obvious or known use cases they had when they implemented that, right? And I think that's totally fine. And as with every software, I guess this is also something that needs a feedback cycle, right? So the community says like, oh, we would like to do that, or we would like to do this. And then they say like, yeah, okay, that's easy to implement, or yeah, maybe that not, maybe this is something for Scala 4, and I think this is just the normal way of developing. I just find it fair to let people know that the simple examples might look simpler than the stuff that you would like to do for a more complex library or something like this.
Absolutely, yeah, no, totally. And yeah, I mean, but I think people are just kind of starting to use Scala 3 a little more in production. At least maybe I'm just speaking for myself. I'm just using it more and more excited about it. I don't know. It feels like it's crossing the inflection point to being at least usable for someone, I don't know, in my position. I'm sure that there are a lot of people who are just like, I want to wait until it's perfect. But yeah, no, I completely agree with you anyway. I'm not arguing. But yeah, that's great. What's your name, by the way? Are you Phil?
No, I'm Nabil. We
oh my God, Nabil.
Before. Yeah.
Oh yeah, no, we totally talked before. Okay, cool.
Yeah, but I have a flu, so maybe you didn't recognize my voice.
I have a flu too, Nabil, and this stupid Zoom thing, I can't tell anything from anything. But yeah, no, okay, great talking with you, Nabil. Yes,
but just FYI, so I also use Scala 3 in production, and I think it's fine. My biggest problem is actually not these things, because I think this is anyway like quite a subset of developers that will use this anyway. Like writing a Scala 2 macro, also not everybody did that, right?
Yes.
My bigger problem, I would say, with Scala 3 is IDE support, like especially IntelliJ.
Well, you can tell where I am. I'm not in my comfort zone. I'm usually in IntelliJ. Now I've run over here just because. Yeah, sorry.
Yeah, no problem. I just think I would not say that Metals is much better, but it shows you less errors, which is less confusing.
And it can calculate these things. So IntelliJ wouldn't, I believe, maybe it would be able to do this one. It couldn't do certain type level calculations where it doesn't work with transparent, basically, because it has its own compiler. And I can only imagine how complicated transparent things are. So
anyway, thanks for today.
Oh, my pleasure. And thanks for chatting.
Yes, thank you.
For fun. Yeah.
Would you be able to share that macro, please? Because
yeah, of course. I've got the debug macro. I'll share. Yeah, I'll put this whole thing up online, and it has all the macros in it. So I'll do that. That'll be the simplest.
I would also suggest maybe to link this in Discord, because it's more persistent than Zoom, right?
Oh yeah, I would not. I'll link it there.
And maybe in the show notes from the YouTube later on.
Yeah, that's actually a great idea. And the Zymposium GitHub. We have many neglected outlets for links. But yes, I'll certainly post it in the Discord, and I'll try to remember to post it on the YouTube. And thank you everyone for hanging out for the last little while. I definitely like being able to talk with people, and having the Zoom chat on the screen is really nice. Having a bigger screen, oh my God, I don't know, I never got a real monitor before. I can see things. I can see everything. Anyway,
have a nice weekend, and you too, Nabil. Thank you.
Okay, you too, Phil. Okay, you're Phil. I got it now. Take care, everybody.